Here's an example of motional electromotive force, the Faraday disk dynamo. A disk of radius r lies in the xy plane, so we've got the y-axis and the x-axis, and the z-axis here is going through the actual axis of the disk. You can see it's rotating here with angular velocity w about the z-axis. The disk is in a uniform constant B field, so we've got this constant B field coming out here. Consider a short portion of a narrow radial segment. So we've got this little bit of this segment of dr. This velocity of this little segment, remember the motional velocity here is v equals wr. Remember w2 pi f, f is 1 over seconds, so the units here is meters per second. So this is the motional velocity, okay, so this is the actual velocity if we measured it, and by obviously the larger the r, the greater the motional velocity here. And since this velocity v here going round this circle here is at right angles to this magnetic field B, the magnitude of v cross B, I've drawn this now in a bigger version, you can see the B coming out towards us, so that's coming out of the page. The v is going around the circle, and you can see that if you cross v with B, so in other words, if you turn v clockwise, you're going to come out. You're going to come, right-handed set. So if you turn that clockwise, you're going to come out. Yeah, the same like if you go from V and you turn a screw into B, you can see that you're coming out. You're undoing it, sort of thing. So that way you're coming out. V cross B points radial outwards. So for this little segment here, the motional EMF is given by dE equals V cross B dl. Okay, where dl this time is the little bit of dr. We end up with omega r, the magnitude of the magnetic field B, dr. We want the EMF from the centre of the circle to the rim itself. So from the centre of the circle, r is 0, and out here we know that the radius of this disc is capital R, so we can just form the, remember we've got dr here now, so we've got a little bit of dE, dr, we can just form the integral between r and 0 here. So if we do the integral, obviously we know that V cross B is VB, so we know that it's WB R squared over 2. That then is the total EMF from the centre of the circle to the rim. For this one segment, we've got the EMF equals WB R squared over 2. But all the radial segments of the disc are in parallel, so you've got all of these radial discs all like that, all the way round. So the EMF between the centre and the rim is the same as that in any of the radial segments, so you're still going to get that potential difference is going to be the same all the way around. Thus the entire disc is a source, and the EMF between centre and rim equals WBR squared over 2. The source can be included in a closed circuit by completing the circuit through sliding contacts of brushes. So you can see here I've put in these brushes here between A and B here, and so we're completing a circuit here, so you can see that because there's an EMF, you're going to have a current flowing through here. This is a higher EMF than the centre, so current's going to flow through this resistor and back up to here. That's how that works. The EMF in such a disc was studied by Faraday. The device is called a Faraday disk dynamo or homoplanar generator. So I've just written in summary here, so with disc above within a constant field B and a fixed radius r, if we increase the angular frequency omega, the voltage between A and B will increase. Obviously, say the VAB here is equivalent to the electromotive force, and that is WBR squared 2. So the faster we spin this disc, the bigger will be the potential difference between here and here, so you're going to get more current flow. So the faster it flows, the more current will flow. This part here is spinning faster. It's going to be moving faster than the inner bit, so it makes sense because it's moving faster against the magnetic field. Obviously that's going to induce a bigger EMF. So that's a really good example of showing how the magnetic field crossed with the velocity of a conductor will give you an EMF.